sort of the more realistic answer is that the thing we want to do, what we really want to do is to rule out the things like deadlocks and live locks, which are hard to diagnose and fix, like sort of the difficult part of concurrent programming. And by making this language terminating, we've ensured that you can't mask deadlocks and live locks in the design with, like, you can't conceal them behind like just an ordinary like looping function. So if you implemented a language like this, you'd probably want ordinary recursion in the language somewhere. If you're ambitious at some type that tells you it might not terminate, but like for the design of these languages, I think you do want to look at terminating calculi in order to prevent you from like sliding hard problems under the carpet.
I think that's kind of leads to my question. So with traditional event handlers, if any of the callbacks fails to terminate, then the UI gets responsibility for your code. Mm-hmm. So you haven't quite solved that, but I guess you could actually, right? I mean, if you ensure that all the callbacks are terminating, then control would always go back to the event.
Yes. So the question was, can you ensure that all of the event handlers actually terminate, and then ensure that the system is like sort of productive and always responsive? And actually, we do ensure that, or at least we believe we ensure that all the callback handlers actually terminate, unless they come from the underlying runtime system. However, like this doesn't guarantee responsiveness because you have the ordinary lambda calculus here, and you can write, even without recursion, programs that require towers of exponentials to terminate. So I've talked with some experts like Marco Gabawardi about using these resource-bounded logics to control that, but I haven't pursued it because like there's this more basic problem of like how do we ensure termination at all?
Two quick ones. So to come back with the data flow programming techniques, there is a notion which is very common. It's the notion of clock, which somewhat describe at which time some stream of events should be considered. And I think that's a very natural solution to the problem of problem distribution that you don't want an event loop to happen when nothing happens. So have you considered this?
So the question is, in synchronous data flow languages, there's this notion of clocks where different streams can run at different rates. So you may have things like a network socket which produces data very quickly, and a UI stream that produces events very slowly. And the answer that so we have considered it, and other people like Bob Atke and Connor McBride have some papers about how you would introduce multiple clocks to a calculus like this one. So basically, instead of having a single next step operator, you'd have a whole family of them all indexed by clocks. I haven't pursued this because I'm sort of interested in the question of how do you relate these stream languages or reactive languages to the traditional callback-based APIs. Okay.
About causality, do causal models have anything to offer here?
Okay, so the question is, do causal models like event structures have anything to offer here? And the answer is maybe. So the model of time in LTL is extremely simple. It's just a linear sequence of events, and so far, so far, I haven't needed anything more than that because the whole story has been I solve one obvious problem and that leaves like 6 more obvious problems to solve, and so now I think we're down to the last 1 or 2 obvious problems, and once we solve those, then it'll be time to look at the non-obvious problems. So at that point, maybe fancier models of causality would help.
Thank you very much.